3 or 4.
All right. So here's what I want to say. So obviously, like you guys have heard that I didn't count these. We're just going to use it as a learning experience. Now, will you see this stuff again on the final? Yes. Will it be on the AP exam? Yes. Don't want to go through some of this stuff from some of these test questions and kind of talk about what we should have done and what are some of the things that I saw that we did that we could have done better with. Yes. We're not going to do any more content, so these last 2 sections that I had kind of hoped to get to, we're just going to bag. We'll cover them next semester or whatever. We'll make some time. So I don't need any homeworks turned in from you guys for 4.5 or 4.7. I trust that you guys will do them because you'll certainly still see that kind of stuff on the final. But I don't need you to, on a week that is probably going to be pretty hectic, don't need you to make some time for some calculus homework that, just it's good enough. Okay? So I went in this afternoon, I went in and put in all the doubles and stuff. If you haven't contacted me about what you wanted to do, I just put a double in, and if you change your mind or you want to do something else, you should contact me or whatever, and I can change that. But barring any missing work coming in or electing to do a retake instead of a double, your score going into the final, you can see. And then I want to spend a little bit of time talking about some of these questions from the test here, okay? So I'm going to look at the no calculator part first. And I'm just going to kind of pick and choose some of the problems that I saw that were some of the most problematic stuff. Yeah.
Sorry, this was a question on the retakes.
Sure.
Do you include the original curve on the retake if you choose to do that?
Yeah, it'll probably be comparable to it. Like I think the test 3 version that I wrote is shorter, so that probably not the exact same curve, but there'll be some kind of curve for it. Does that?
Yeah.
Okay, sure. So I want to look at multiple choice question number 5 to start. I saw lots of us take like a whole sheet of paper working on this thing, and this.
That was me.
Yeah, it was. No, you weren't the only one, Chanel. Shouldn't have been that long. So let's take a look at this and do this. So you'd want to start by doing what? Feel free to answer when I ask questions like these. So number 5, you'd want to start by doing what, Christian? Yeah, let's do a direct substitution. When we do that, we get natural log 0 over natural log 0, right? What is natural log of 0? Not 0. Well, we need it. It's negative infinity is really what you want.
Yeah.
The way I remember that is if you think about what the graph of the natural log of 0 or natural log looks like, there's a vertical asymptote at 0 and the graph points down. That's how I remember that it's negative infinity. But the point of the matter is it's indeterminate and it's in the form for L'Hopital rule, right? So that's what I'm going to choose to do first. So what's the derivative of the top?
1 is 4 plus cx.
Okay.
Times 4ax to the third plus c.
Great. And then the denominator, what's the derivative of that?
1 third dx to the third plus dx times 3 dx squared plus c.
Great. So far, so good? Most everybody that attempted a L'Hopital rule did that part correctly. So what I'm going to do now is I'm going to simplify some stuff, right? So I can think about this as just like one fraction over another fraction, right? Oops, forgot the limit there. We'll have to squeeze that in.
I think this was slightly different than the one that.
Yep, depending if you took it late or not, you might have gotten a slightly different one.
Oh.
So there's two versions floating around, but it's like the same idea.
Okay.
Like most of the problems are basically the same problem with like minor variation to them.
Okay.
Now, I got a fraction stacked on top of another fraction there, right? Let's simplify it better than that, because I'm not real excited about the prospect of having to do two quotient rules here. Are you?
No.
You shouldn't be. How do you simplify a fraction stacked on top of another fraction? Yeah, so the top would be 4a cubed plus c times the denominator of that bottom fraction. And then we'd have the bottom of the top fraction times the top of the bottom fraction, right? Oops. Is everybody okay with what we did there? Now what should I do? Who has an idea of what to do next?
Can you multiply the top and bottom by like FOIL and round?
I liked your first idea better. So the thing to notice would have been here and here. What do you notice about those two parentheses?
X.
Yeah, you have a greatest common factor of x there. And now look at what we have. If you do a direct substitution, what do you see? It's not indeterminate, right? Because I multiply that or divide that x out of there, reduce that x out of there. Now when I do a direct substitution, I am donezo. And what should this turn into then? Chanel?
So could you have applied L'Hopital's rule without simplifying it? This would have been more complicated.
If you would have done L'Hopital again, you would have been doing a lot of algebra for a while, but I think it would still end up working. But again, time matters, right? Part of the reason why we're running out of time taking the test is we're missing these off ramps to take a problem that could be a 10-minute problem and turning it into a 2-minute problem. Because doing two product properties here and then trying to clean up whatever's left over and then do a direct substitution again, it's going to get pretty rough and pretty time consuming. Even if you chose to FOIL that out and then do a L'Hopital on it, or at least it's all polynomial, probably would have been a better option than leaving it in the factored form. But it's still going to be like extra time consuming. Yes, it's one more L'Hopital step, and you should end up at the same spot, but look how quick that was when you saw what to do there. So again, L'Hopital, excellent option, but there's often going to be an off-ramp after one or two of these where doing some reducing is going to get you home, kind of thing. You know what I mean? I would be surprised on an AP exam if they expect you to do, more than 2 L'Hopital rules in a problem. If I started to try to use a second or a third one, even a second one, I would be dubious and be like, am I sure I couldn't find an easier way to do this? So let's look at the next one. I want to look at 6 here. I did not think 6 would be as difficult as it turned out being. But this turned out to be quite difficult. So I gave you this piecewise function and asked you to start by telling me or showing me that this was continuous over its domain. To show that a piecewise function is continuous over its domain, what do we need to do? Christian. Great. So what Christian is saying is, first we need to show that each part is continuous over its domain. And then we need to make sure that the end of one part lines up with the start of the next part so that these things are all hooked together, right? So right away we can say, we can make that a bracket. So right away I can say, okay, well, from -2 to 1, from 1 to 3, and then from 3 to 5, f is continuous because
They all fill in each other.
they're polynomials, because f is a polynomial. Now, it's a different polynomial in each of those parts, but that doesn't matter. It's polynomial, so I know we're continuous. The question becomes, what about x equals 1, and what about x equals 3? To show that we have continuity at the point, we need to show the limit as x approaches 1 of f of x equals f of 1. Well, f of 1 is easy. That's 0. To do the limit as x approaches 1, we have to be careful here because it's piecewise. So what's happening on the left-hand limit, we have to show is equal to what's happening at the right-hand limit. So again, we get 0 there at the left. And then I saw a lot of you guys it looked like a lot of time trying to plug in values to this. What would be easier than trying to plug those into that quadratic? You don't have a calculator. So,
You factor that?
yeah, that's what I intended for you guys to do. So if I pull out that greatest common factor of 5, I notice, hey, that's an easy quadratic to factor. So now plugging 1 into that is trivial, right? The 3 is the part where I felt like people really lost some time trying to plug the 3 in here in another step. But and since those two things are equal, we know that we got it, right? The left-hand limit's equal to the right-hand limit, which is equal to 0, which tells me the limit is equal to 0, which is what f of 1 is equal to. That's what we needed. Same idea here for 3. If I want to do f of 3, well, hey, that's really nice that I factored that, because boy howdy, I can see that f of 3 is 0 real quick. Didn't take much time at all. And then we'll look at that same limit to make sure the left-hand limit is equal to the right-hand limit. So again, the left-hand limit is that same thing that we just plugged in. Why am I able to just plug in these limits? Right? Like I'm just doing direct substitution to evaluate these limits. How do I know I'm able to do that? Yeah, because the limit is continuous on that side because it's a polynomial. I can just do direct substitution. Now I can't do it for like the limit as x approaches 1 or the limit as x approaches 3 because it's at the boundary between them. But from the left, it's all just on one polynomial, and from the right, it's all just on the other polynomial, so I can direct substitute those. Now, there's a little bit of writing to do, but it should have been pretty easy. That's really like a chapter 1 question, what we saw right there. And the reason I asked you to do this is because we needed this for parts B and C. So part B wanted the derivative. So since f was a piecewise function, its derivative should also be a piecewise function. And to get the pieces that I need, I can just take the derivative of, bless you, each piece. But I need a domain now for each piece. Okay? So let's think about what this will be now. If I go back to the original, this is going to look like, so we started here, oops, did an open, and then it did like one of these, and then we did like one of those, right? Kind of looks like that. Can I take a derivative at that point? No, why not? There's no left-hand limit. Remember, a derivative is a limit. Since the function has no left-hand side, there's no left-hand limit. We can't take a derivative here. And likewise, we can't take a derivative there. Correct? So automatically, I know that my first domain should be that. Can I take a limit here or a derivative there?
Yep.
No.
Oh, sharp corner.
It's a sharp corner. Likewise here, correct? So my function or my domain should look like this. Now, suppose you didn't try to graph what f looks like. How would I know that those are sharp corners without having graphed it? Was that going to be your question, Chanel?
Yes, actually, yes.
Okay. So this is what I would do. So the endpoints, the start and end of it, we know those are going to be undefined in f prime. These transitions from one piece to the other piece, we don't know. At least not without at least looking at a picture or doing this algebraically, which I'll show you in just a second.
Should the derivative be negative 2x, not negative?
Yes, thank you. Of course it should. Okay, so what I'm going to do is I need the slope from the left equal to the slope from the right. And because these are polynomials, I can just plug it in. And I see that, no, the left-hand slope doesn't equal the right-hand slope at 1. That's a sharp corner. The derivative isn't going to exist there. Yes?
Wait, why are you saying the slope, like, but you're taking the limit? Like, I don't understand.
I'm taking the limit of the derivative. What does the derivative give you? The slope of f.
Oh.
So the slope from the left at 1 is different from the slope at the right at 1. That means it's a sharp corner. And I could do the same thing here. This is how you would algebraically do this. I would have accepted a graphical argument here. I don't know between the two sections that anybody made this observation. Everybody okay here? Okay. I saw lots of us just copy the domain the same from f to f prime. You need to be careful about that, especially if it's a piecewise function, right? You have to worry about the corners, and then if it's defined over a closed interval, you lose the closed when you take the derivative. That will always be the case. All right, part C asks for the critical numbers. Well, right away, without doing anything, we know two of them. What two critical numbers do we know right away without doing anything more? 1 and 3. Why is that, Christian? That's 1 and 3 are in the domain of f, but not in the domain of f prime. Everybody's okay with that? Yes.
Wait, I thought it's because the derivative didn't. Well, no, it doesn't. Oh,
That's the same thing as saying the derivative doesn't exist if they're not in the domain,
Okay.
right? Those are the values. The derivative is undefined. It fails to exist. They're not in the domain. 3 ways of saying the same thing. Okay. The other place we need to check is where the derivative is equal to 0. So we can check that. We look at where negative 2x is equal to 0 from negative 2 to 1. Well, we get x equals 0, and that's in there, so that's okay. We'll add that to our list. We have 10x minus 20 equal to 0, and that's got to be on 1, 3. I get x equals 2 there, and that's on in between 1 and 3. So that goes on to our list. And then our last one is negative 3 equals to 0. And that should be between 3 and 5, but that has no solution anyways. So those are going to be my critical numbers. Notice that I didn't include negative 2 or positive 5, even though they were defined for f and undefined for the derivative. Why didn't I include those ones? Well, they were in the domain of f, and they weren't in the domain of f prime, but why didn't I bother to include them? It wouldn't be wrong if you did. Well, if I'm using the critical numbers to find local maxes and mins, where is negative 2 and positive 5 at? Yeah, they're the endpoints of our function, so they can't be a local min or max because they're the ends. They could be an absolute, and we would have to check those if we're checking for all types of minimums and maximums, but we can cover that when we get there. But I wouldn't need to list them per se as a critical number. So far, so good? Then it says determine the minimum and maximum values, both absolute and local, for f on the interval from the closed interval from negative 2 to 5. So since it's a closed interval, let's do the absolutes first. For the absolute maximum and minimum test, what do we need to check? I need to check the critical numbers and the endpoints. So I don't need to do increasing and decreasing for that. Where was it? So I'm just going to go ahead and plug these in now into the appropriate place.
Is this into the original function?
Yes. Oops. Oops. All right, that's -5. And then oops, and then we need to do 5. So I can see that I have an absolute max at, where is it? It's here. And an absolute minimum at that. Everybody's okay? So this and this I know can't be locals because they're at the endpoints of my function. But this one, because it's an absolute maximum, I know is also a local maximum. And now I have to check the other 3 doing a first derivative test. Or actually, let's do a second derivative test. That'll be much easier.
Wait, Mr. Cole, how do you know that 16 is a local maximum?
Because it's an absolute maximum.
No, f of 0. Why is it a local maximum?
Because it's an absolute maximum.
Wait, I don't get it.
So like,
Oh.
you know, like I have this. That's absolute because it's the highest, but it's also local because in its neighborhood it's the highest.
Okay.
So long as it's not at the end, start or end of your thing, it can be a absolute. It will be absolute and local.
Okay, how come f of -2 and f of 5 are highlighted?
Because those can't be locals because they're at the endpoints. So all I did here was I did the second derivative because it felt to me like that was going to be easier than trying to plug decimals into f to do a first derivative test. And the thing that I love is that about this is that the second derivative is constant over these intervals. So let's look here. Well, f of -1, well, that's supposed to be a -1, wasn't it? Or is that supposed to be regular 1? Oh, that's a weird order I wrote them in then, Mr. Kulik, whatever. Okay. If I do f of 1, why did I? Oh, that interesting. I guess I have to do that the other way, but this one I get for free with the second derivative, right? F of 2 lives here. Because the second derivative is positive, what does that tell me?
It's calculated
So it's a local min. Oh, that's right, of course. So these two, why won't these work for the second derivative test? Yeah, because the second derivative test requires that the first derivative is equal to 0, not undefined in this case. So these ones we would have to check with a first derivative test, which is fine. You could do the whole thing as a first derivative test. So I'm going to do like a half and then like 1.5. So my other one, 3. So there I'm going to do like 2.5 and 3.5. Sound good to you guys? So if I do 1/2, that's going to be 1 minus 1/2 squared. I'm sorry, I have to do f prime now. That's negative 2 times 1/2, that's negative. 3/2 is 15 minus 20, that's negative. So that's nothing, right? And if I go back and I looked at the picture I kind of sketched, that should make reasonable sense. And I plug the 2.5 in, that's going to be, oh no, it won't be negative. Yeah, it will. Okay, yeah, 10 minus, that's right, okay. So that would be 25 minus 20, so that's positive. So I have a 2 in here somewhere, right? And then 3.5 is down on the next one, so 9 minus 3 times 3.5 is negative. So that should be a local max. Did I do that right? I don't feel like I did that right. Yeah, I didn't. But that's negative everywhere there. That's okay. So I think that's it. You gotta be careful there though, right? I want to do the related rate here from the version 2 because this one there was all kinds of like weird, people gave me like just weird answers for stuff. Now the version 1 related rate problem I think people had a much better or much easier time with. I didn't see as much weird stuff happening.
Not me, Mr. Bowen.
Well, in comparison, you did. You did do less weird stuff. So here the question reads, a sculptor uses a constant volume of modeling clay to form a cylinder with a large height and relatively small radius. The clay is modeled in such a way that the height of the clay increases as the radius decreases, but it retains its cylindrical shape. At time t equals c, the height of the clay is 8 inches, and the radius of the clay is 3 inches. And the radius of the clay is decreasing at a rate of 1/2 inch per minute. At time t equals c, what is the rate of the area of the circular cross-section of the clay? What rate is the area of the circular cross-section of clay decreasing with respect to time? Show the computations that lead to your answer, indicate a unit of measure. Circular cross-section. Area. What equation should we be starting with?
Pi r squared?
Yeah. Now, I didn't write that down in the problem, but I don't think I should have to, right? Okay. And then if we take the derivative with respect to time of both sides, I have that. And at time C, it tells me the radius is 3, and the rate is -1/2. So it should be -3 pi. And what unit should this have?
Something for time.
Excellent. Inches squared, because it's an area, and it should be per minute. I know that the linear units were represented in inches per minute, or the linear rates anyways. So that's all you needed to do for that. I intended that to be quite easy. And that's okay if it wasn't. Hopefully it looks easy now. Says at time C, at what rate is the height of the clay increasing with respect to time? Show the computation that leads to your answer. Indicate the units of measure. Note the volume of a cylinder is, or with radius r and height h is given by volume equals pi r squared h. So what should I do to start here? Just going to differentiate both sides with respect to time. What's the derivative of v with respect to time? It is not dv over dt. Yeah, you missed that. We have a constant volume. So what is the derivative of v with respect to time? 0, because it's a constant. To differentiate pi r squared h, what do I need to do to differentiate that? Product rule. So I have pi times the derivative of r squared times h plus r squared times the derivative of h. Everybody's okay there? We know at time C, r is 3, dr dt is -2, or -1/2, h is 8, and we're solving for dh dt. And it should be fairly straightforward from there, right? Now it's just algebra time. Everybody's okay? This last one, part C, I don't know that anybody even started it correctly. I think basically because of, and the issue I think was reading. So let's read this together. Write an expression for the rate of change in the radius of the clay with respect to the height of the clay in terms of h and r. What is it asking us for? Symbolically, what is the name of this variable that it's asking us for? It's asking for dr dh. Notice it's asking the radius of the clay with respect to the height of the clay, right? That's what we're looking for. I don't think anybody started by differentiating with respect to height. When I differentiate v with respect to height, what do we get? Chanel?
I have a question on the previous one, actually.
Okay, can you just hold on for us while we're in the middle of this one? Nope. You're very close, though. It's easier than that.
0.
Volume is constant, so it's 0. Now, again, we'll do a chain rule, or I'm sorry, product rule. And since I'm doing differentiating h with respect to h, all I get is a 1. I get no dh over dh, right? And so now all I have to do is do some algebra to get dr dh by itself, and I'm done. Is that okay? So again, like, really have to read the problem. The trick there was recognizing what derivative they were looking for. I think everybody that tried this problem did differentiate with respect to time. And we should have caught that just from better reading, right? Pointing this out to you now so that we can do a better job in the future if we run into a problem like this. Got to be careful about reading what we're looking for. Okay. Chanel, you said you had a problem with the previous one.
Yeah, sorry about that. So, why didn't you like finish the problem? Like.
Because all that's left is algebra. You just have to get the dh dt by itself.
Oh, okay.
That's all. Is that okay? I just figured at that point we're good to stop, right?
All right.
Okay, looking at part 2, we definitely need to do one of these, or do these L'Hopital rule problems, because they, surprisingly, I thought that this would go well, and they didn't really go that great. Okay, what's the first thing we do? Yeah, you do a direct substitution, right? Oops. So that's in our indeterminate form of 0 over 0, right? Is everybody okay with how I got the values when I plugged in? Okay, so let's do a L'Hopital. What do I get when I do the derivative of the top? What's the -1 from? The chain rule, right? We had to do the derivative of -x there. When I do the derivative of the bottom, what do I get? Okay. Everybody okay? What do we get when we direct substitute now? Still indeterminate. What should we do? L'Hopital again. What do I get as the derivative of the numerator?
E to the x plus e to the negative.
Times -1. And then the denominator? Nope. Sine x. Okay.
But so why'd you want that -1?
Chain rule.
But isn't it when you bring down the -1 for that one, it's positive? So we'll just be like
So the previous step had 2 negatives. The next step will have 3 negatives,
Got it.
right?
Sorry.
That's
sorry.
okay. Is that okay? Okay. What do we do now? Direct sub it. No, didn't do it. What do we do? Have we seen any exit ramp anywhere where we could have factored and reduced? Should be obvious that we can't because we have trigs and exponentials. And there's not really any opportunity there. I'm just going to skip a little bit. Everybody okay with how I got to there? If I direct substitute now, what do I get? That negative x in the e to the x, I think, screwed a lot of us up. And then a lot of us hung on to our constants through differentiation, it seemed like. Saw that mistake happen a number of times. Where we did the derivative of 2 and the 2 stayed, or the derivative of 1 and the 1 stayed. Let's do the other one. Now this one I ended up changing on you guys, right? What is it that I had you change this to again? And what was the limit going to? Infinity, right? Yeah, okay. Okay. So what do we do first? Do a direct substitution, right? So I get infinity times 0. That's one of our indeterminate forms, which if you attempted this problem, most of us saw. But in order to use L'Hopital's rule, can we do it if the indeterminate form is infinity times 0? No. We need to write that as a fraction. What is going to be the best way for me to do that?
X squared over e to the x squared.
Yeah. Now we can, if we direct substitute now, we get infinity over infinity. So we're ready to L'Hopital. So that's going to give me 2x on top. And then we're going to have e to the x squared times 2x on bottom. Is that okay? What do you notice? You can just reduce. So if I direct substitute now, I have 1 over infinity, that's just 0. That one was easier in a way since you only had 1 L'Hopital to do, but you had to massage it a little bit before you could L'Hopital it. I saw several of us try to just do the derivative of the product and then take the limit again, and it doesn't work that way. L'Hopital, you have to have a fraction. Has to be 0 over 0 or infinity over infinity or positive infinity over negative infinity or negative infinity over positive infinity or negative infinity over negative infinity. The type of infinity doesn't matter. If you have infinity something over infinity something, that's good enough to L'Hopital it. Let's see. And then this was the next one.
This one was like the one on the FRQ.
It was like the one on the FRQ with a little bit of difference here in that it's e to the negative fx. or in the other one, I think, was it e to the 2fx? Is that what I did?
No, actually, this was just e to the f of x.
Okay.
It was like almost exactly.
Okay. The graph is harder. That's the difference from the FRQ. This is a harder graph.
Yeah, I don't know. Honestly, I just found it like the same kind of idea.
Yeah.
Like,
Okay. So if we want to get the graph of the tangent of g at 0, I know that my y coordinate that I need is going to be g of 0, which is e to the negative f of 0. We're told f of 0 is 3, so that's e to the negative third. And my slope should come from g prime of x, so that's e to the negative f of x times negative f prime of x. So the slope at x equals 1 is going to be g prime of 0, which is e to the negative f of 0 times negative f prime of 0. And f prime of 0 is negative 1. So I have like negative times negative 1. So I have y minus y1 equals m times x minus x1. If you wanted to clean that up some more, you could have, but you didn't need to. So far, so good. So here we're asked to find the values of x in which g has a local minimum. So if we want to do that, we have to look at where g prime is equal to 0. Well, I know g prime is negative f prime of x times e to the negative fx. And I set that equal to 0. If I apply the zero product property, I know I divide both sides by negative 1. I have this. And now I can just go to my graph and read off the places where the derivative is 0. So negative 2, positive 2, and 7. And this is an exponential equal to 0, so it has no solution. So far, so good. Now I'm going to make myself a sign diagram. And remember, I'm looking for g prime of x. So what I'm going to do is I'm going to start by writing down whether f prime is positive or negative on these intervals. So less than negative 2, f prime is positive. And then we're negative, and then negative again, and then we're positive at the end. Okay? So if I take a positive value for f and I plug it into here, this part is always positive, right? Because it's exponential. That part I have a negative times a negative, so that part, or I'm sorry, positive times negative, so that makes g negative. Everybody's okay with that? And hopefully it should be pretty clear from here now. G is just going to have the opposite sign of, G prime will have the opposite sign as f prime, right? Can we see that? doing the same kind of manipulation. So we've gone from different color, decreasing to increasing. That's a local min. Here we've gone from increasing to increasing. That's nothing. And then here we've gone from increasing to decreasing. That's a local max. So our local min should be -2. Is that okay? Part C was like, this might have been my favorite question on here, because boy, you really had to know what you're looking at. Of course. So we would start by saying, okay, well, we have the first derivative of g. If I want the second derivative of g, I need to do the product rule. And this you should recognize, we've done this particular product rule with a chain rule in it like a couple of times now. Yeah, good luck tonight.
Thank you.
Yeah, go get some buckets or something. So I have this. Now, notice that the question is just asking for positive, negative, or 0, right? So that's all I'm going to be worried about for each of these pieces. If I look at this exponential piece, I know that has to be positive. Everybody's okay with y?
Yes.
Oh, now we have to, sorry. Let's do g double prime of 2. Not that it changed much, but and I know that's positive just because it's exponential. I don't really care because I don't have any clue what f of 2 is. If I look at the derivative of f at 2, well, that I can calculate just from the graph. That's 0. And now how do I find the second derivative of f of 2? Or the second derivative of f at 2, I should say. Well, let's go and look at our graph. Notice that on f prime, 2 is a local maximum. If I look at the derivative of this graph, what would the derivative of this graph be at x equals 2? 0, because this is a local maximum. We know any graphs, the extrema, if you look at the next derivative down, those extrema should be zeros, right? So 0 minus 0 is 0 times something positive. still 0. The rate of change for g prime of x. Well, if I want the average rate of change, should just be that, right? If I want the average rate of change for g prime, it should just be the slope for g prime. Okay. Well, I know what g prime is, right? That's negative f prime of 7 times e to the negative f of 7, then minus, and then we have a negative f prime of negative 2, e to the negative f of negative 2, all over 9. Now what's f prime of 7? If I go to the graph, 0. And what's f prime of 2? Or negative 2? 0. So do I care about what those exponentials are turning into? I do not. That's just 0. Again, a lot of us used f prime instead of g prime. A lot of us use g instead of f. Or I'm sorry, use g instead of g prime. And it's all kinds of, it seemed to be like problems just with slowing down and reading the problem of what it was asking. Okay, next up was 15, and this one I hoped was going to be one of the easier ones since it was, you had your calculator, even though there's some trig stuff in it. Oops. I think those of you that got the version 1 test, I think the version 1, the algebra was a little bit, there's more answers and stuff to places. I think you had more extreme in there.
I don't know, Mr.
But-
Flynn, I did this like when I had to leave, so like.
Yeah, it's okay.
rushed through it.
So we're asking for where f is increasing or decreasing. To do that, we need to know where it changes from positive to negative. Ostensibly, we need to find the zeros, or the place where the derivative is 0. So I'll start by taking the derivative of f. What's the derivative of sine squared?
2 sin x times cosine x.
Great. So you had to chain rule that. A lot of us missed that. And then the derivative of 2 cosine x is?
Negative sin x.
Well, 2 times negative sine x, but yes. And then we'll set that equal to 0. And how am I going to solve this now? Yeah, let's make it a 2 sine. Is that okay with you? I don't think you'd have a problem with that. Now that's in factored form, we can apply the zero product property. What are the solutions for sine x equal to 0 from 0 to 2 pi?
3 pi over 2.
0, pi, and 2 pi, because it's closed at 2 pi. Right, so we need all 3. And then here, cosine x would be equal negative 1. What values of x is cosine equal to negative 1? Pi. Which is fine. We got a duplicate solution, no big deal. So we'll go ahead and 0, pi, and 2 pi. We'll make our intervals of increasing and decreasing. Now I don't need to pick anything left of 0 or anything right of pi because those are the endpoints for my interval. So hopefully pi over 2 and 3 pi over 2 seem like the easiest test values to pick. So when I plug in pi over 2, sine of pi over 2 is 1, but cosine pi over 2 is 0. So I'm left with just 0 plus 2, so that's positive. When I plug in 3 pi over 2, sine is negative 1, but cosine is 0, so I'm left with 0 minus 2. So we're increasing from 0 to pi and decreasing from pi to 2 pi. Everybody's okay there? If you got through the algebra there, it shouldn't have been too bad. Next, it asks for the local minimum and maximum values for f. Well, we know that this is a local maximum because we're going from increasing to decreasing. So we're just doing f of pi. So that was sine squared. Sine of pi is 0. And cosine of pi is negative 1. So there's my local max, and there's no local min. For part C, we asked for the inflection point and intervals for concavity. So here we're going to need a second derivative. What do I get when I take the second derivative? So I have sine x times negative sine x plus cos x times cos x plus 2 cos x. Everybody okay? So I'm going to have 2 cos squared x minus 2 sine squared x plus 2 cos x. I'm going to set that equal to 0. How am I going to solve that? What do you plan on factoring? There's no greatest common factor, right?
Can you put in your calculator?
You could have done that. This also, you could do this without. This is a normal trig solving problem that we would have done last year.
Is there like a identity?
There's absolutely an identity you would use here.
Is it 1 cosine squared x?
Well, it's not plus.
Oh, okay.
So this is what you do. Which one of these is not like the other?
Sine.
Sine. I know sine squared is the same as 1 minus cosine squared.
And then you would multiply it out, and then you're able to factor?
Yeah, so if I clean this up, I have 2 cosine squared x minus 2 plus 2 cosine squared x plus 2 cosine x. So if I combine my like terms, and I'm going to divide both sides by 2. Just to reduce the coefficients, make them a little bit smaller. Now what am I going to do with that?
Factor.
Yeah, so that should look like what kind of thing?
You would have to do 2 times minus 1, like the AC thing.
Yeah, should look like a quadratic. We're not going to do all that long factoring because there's only like a couple of possibilities. We're just going to kind of guess and check it. So we know that the first thing has to be a 2 cosine and then either plus or minus 1, and the second has to be a cosine and then plus or minus 1, right? We just have to figure out which one is the plus and which one is the minus. Where should the plus go and where should the minus go?
I think. Minus. Plus or minus.
Plus in the first one, minus in the second one is not correct. You want minus in the first one and plus in the second one. The trick is that this is all you care about, and seeing if that gets you the positive cosine x or a negative cosine x. So you definitely want the 2 cosine multiplying the positive thing. Is that, you can see that now?
Yeah.
And again, you could do the a times c and add to give you b thing and do the factor by grouping. I just did it by inspection since there's really only like 2 choices, right? Like I can tell everything except for like one has to be plus and one has to be minus. And then I can kind of guess and check that out. So 2 cos x minus 1 equal to 0. And then cos x plus 1 equal to 0. So cos x equal to 1/2 and cos x equal to -1. Where's cosine x equal to 1/2 from 0 to 2 pi? Those are unit circle values. We should be able to do that. Nolan's not here to do it for you. Who remembers their unit circle well enough to tell us where cosine is equal to 1/2? It's not pi over 6.
Pi over 4.
It's not pi over 4.
Pi over 3.
There's one of them. Where else, what other quadrant should cosine be positive in?
4.
4, good. And what is the equivalent reference triangle? 5 pi over 3. So again, the way I'm thinking about it is 1/2 is the short value, so that you're having like something here. That's the biggest of the 3 angles in the first quadrant. The same thing has to be there. So if this is pi over 3, that's pi over 3. Anyways. And then cosine is equal to -1 at pi. So now we have to set up some test values. So that I would pick between 0 and 1/3 is, well, I guess I can just use 0, right? That's in our interval. And then we'll do 1/2. We'll do 3/2. And I guess we can just do 2 pi over here. So when I plug them in, so I'm going to use this as my version of f double prime, because it just makes life so much easier to look at that one as opposed to the first one that we started with. Particularly if I didn't have a calculator. I do here, so it's not that big of a deal. So that's going to be cosine of 0 is 1, so that's 2 minus 1 times 0 plus 1 plus 1, so that's going to be positive. Cosine of pi over 2 is 0, so that's 0 minus 1 times 0 plus 1, well, that's negative. 3 pi over 2 is also cosine is 0, so that's 0 minus 1 times 0 plus 1, so that's negative. And 2 pi cosine is 1, so that's 2 minus 1 times 1 plus 1, so that's positive. So we have inflection points there and there, and then we are concave up from 0 to pi over 3, and then from 5 pi over 3 to 2 pi. And we're concave down from pi over 3 to pi, and then from pi to 5 pi over 3. that was some yucky trig there, but the idea should have been relatively straightforward. And at any of these points, you could have like used your calculator to do the solving and given me a decimal, and it would have been fine. I would have accepted that. And the last problem in here was intended to be like a gimme. So the last part of this asks you to find the C's such that f prime of C is equal to that average value. Well, f of 2 pi, I'm just going back and plugging 2 pi in here, right? So what sine of 2 pi? 0. And then cosine of 2 pi is 1. So that's 0 minus 2, or I'm just going to write negative 2.
Why is it negative 2?
0 minus 2 is negative 2.
Yes, I'm sorry.
It's okay. And then if I do cosine, if I plug in 0, won't that just be the same thing as 2 pi was? Because those are coterminal, right? So I'm just really finding where the first derivative is 0 from 0 to 2 pi. Didn't we already do that in part A? We said the answers were 0, pi, and 2 pi. What's the only hitch here?
Why would you process 0?
Because it's asking for the open interval.
Oh, and they're included.
And those were, before when we solved, it was on the closed interval. That's all. So next time in class, if you guys would, please look through this test 4 on your own. Look at the stuff we didn't talk about yet, or if you have a different version, we can talk about your particular question from your version. And please, please, please look at the optimization homework. Those are the 2 things I want to take questions from next time, and we can talk a little bit more about exam format and what to, what to be studying and how to be studying, kind of what to expect, the content of some of the big free response questions to be drawing from. Okay? Questions for me before we go? Okay. Again, don't lose heart on how poorly this went. When everybody does this bad, it's at least, it's at least half of it is my problem as opposed to just your problem. It'd be one thing if people were still capable of doing well and nobody really was capable of doing well here. So that tells me that maybe things were just too difficult. The things that I chose. So take a little comfort in that at least half of, you can blame at least half of it on me for either writing a poor, a test that was too difficult, or picking too tricky of things, or constructing it in such a way that was too obtuse, or any number of things. So don't quit on me. We're doing okay, even if it doesn't feel like we're doing okay all the time. I think you guys know more than you think you do.
Is this normal? Is this how last year did as well, or are we doing worse?
Yeah, that's what I'm doing.
Let's have one second.
Take a breath. Put yourself in God's presence for reflection. One of the commonalities between all people is the desire to be great. From childhood, we want to play the hero, we want to be someone important, we want to be someone who makes a difference. Even those who don't feel like being great right now, it's likely some kind of some kind of anxiety maybe holding you back. But the desire to be great is there. We are all called to greatness. But what does greatness look like? Greatness in Christianity can be defined as striving to become as close as possible to exactly the person God created you to be. So while we are all called to greatness, we need to be careful not to chase shadows of what other people are doing or have done. We need to ground ourselves in our relationship with Jesus and slowly conform ourselves to the unique ways He is calling us to greatness in our lives. That's all for today, Notre Dame Press. Teachers, you may dismiss your students at the site song. Have a great afternoon, and God bless.
Thank you.
So to answer your question, I would say that I prepared the students last year differently than I'm preparing you guys, based on feedback I got from their AP tests. So are the tests that I've written you harder than what I wrote them last year? Yes, they're more closely based on the kinds of things and the kinds of questions that you'll have to do, that they would be expected to do on the AP exam. Now, I would not have, it's so difficult to say, are we doing better or worse, because I'm taking a little bit different tact about how I'm testing you guys versus them. But I don't think in general you're any stronger, weaker of student than they were last year. It's that I'm taking, trying to use using my feedback from the AP about, raising the rigor in some of these areas so that I can better prepare you guys for the AP exam in the fall or in the spring. And so some of the, sometimes along the way I hit a little hiccup and I go too far, which is what it felt like happened on maybe this test, and the previous test was just too long, I think. And this one was, I think the length was probably okay, but the difficulty was a little too much. But I'm trying to kind of find that sweet spot, and provide enough of both ways to where I'm not you feel just completely defeated, which I know is how we feel now, and I apologize about that. I don't want that to be the case, and still giving you good preparation for what you'll have to do later on. So that's what I would say.
Right.
Is that?
Mr. Foley, how long have you been teaching this class for?
Well, I taught it 2 years, 15 years ago, and then this is the year 2 of teaching it since that hiatus.
Oh, wow.
So it's been a while.
Okay. Bye, Mr. Foley.
Sorry, I feel like